speaker. So first speaker is Professor Heino Falcke. He's a professor of radio astronomy and astroparticle physics at University of Nijmegen in the Netherlands. And he's the winner of the Spinoza Prize in 2011, and he's the chair of the Einstein Horizon Telescope Science Council. And for instance, he was the one that announced the first Einstein Horizon Telescope results, the first image of the supermassive black hole at the galaxy, not our own, in 2019. And today he will announce the project's even more ambitious and challenging results, the image of the so-called Sagittarius A black hole in our own Milky Way. So please welcome Professor Heino Falcke.
Thank you. Thank you very much. I'll give this talk. I'll not share my screen. So if you want to see the background, actually the screen will be on the background. And so you should put me in the speaker view, not the gallery view. So we have, one big size. So, it was long planned I would come to Finland to give some public talk. So this will be a more public talk today. Connection because my book that describes a little bit of this came out in Finland during the corona pandemic, and so it was difficult to come, so everything had been shifted, and I was in Finland a week ago, but then we couldn't get the schedule right, so we do it online now again, but at least this way we can connect a little bit. I'll talk about the entire development, not just the galactic center, but also the M87 results, of course, briefly, as I said, in a very general presentation. Right. So I'm no longer the chair of the Science Council, so just that's what I wanted to correct. So I'm now someone else took over. I was until 2020. And now in the board of the Event Horizon Telescope, and we're still actively participating in this project, which, by the way, in our case was funded by the European Research Council, by a big grant, the European Research Council Synergy grant of 14 million euros, which was made really an impact, which is good because, in fact, I remember the very first proposal that I submitted for millimeter VLBI was in the early 2000s. When I was still in Bonn. And in fact, one of the key participating partners at the time of this proposal was the Metsä-Hovi radio telescope. And so ever since, I've been keenly aware of the fantastic work of millimeter astronomy that's being done here in Finland, or there in Finland, because I'm now here in my place. So let's start very general first about thinking about space and time. 1,000 years in your sight are like a day that has just gone by, or like a watch in the night. Time is relative. This is a very old feeling, a very old sense that people have, going back even to biblical songs, like in the Psalms here. And if you change space, you actually also change your perspective of time. If we go into space, looking back at Earth, our perspective changes. For once, of course, if you go around the Earth, like in the space station, you want to see a sunset every 90 seconds, 90 minutes, and that means that your day changes. The length of your day suddenly changes. But something else changes as well, namely, the precise measure of clocks. If you measure an atomic clock, which for example are the GPS satellites that we use to do navigation, then you find that they actually run faster in space than here on Earth. And that has to do with the special properties of the general theory of relativity that Albert Einstein developed. And the idea that came out is that space and time are not absolutes. They are relative. They can change, because what space and time is something you measure. The question, do they even have an existence of their own? You can't touch time or space. So all we know about space and time is what we measure. And on a fundamental way, how we measure space and time is through the properties of light. How long a ray of light is traveling, or how fast light is ticking, as if we see it as a wave. And And then in further thinking, Einstein came to the picture where we describe gravity as not a force, but something that actually affects space and time, actually curves space and time. So if you put this on a two-dimensional plot like this, and then you have a mass somewhere, it will actually curve the three-dimensional space, in fact, the four-dimensional space-time, but the three-dimensional space, and we represent this here with a two-dimensional flat surface. And that means if you shoot a light ray on a straight path, it actually will have to bend because it follows the curvature of space. And also time will change because, suddenly light has to sort of travel, have to make longer steps, as space is somewhat stretched. And therefore also, at least seen from a distance, the waves seem to stretch. And that means also the time that we measure stretch because the ticks, sort of the steps that light takes, become larger and longer. And so time runs slower the closer you are to a curved, or the more curved space-time is, the closer you are to a geometric body. And very quickly thereafter, Karl Schwarzschild developed a theory, or just a sort of a solution to the field equations of Albert Einstein, and describing how matter would behave, or space-time would behave, if you have all matter compressed into a point. And there were some amazing properties that you would see. For one is, light would be deflected so strongly that it would actually end at some point in the singularity. So it would stop, it would terminate. And secondly, light would be stretched so much that if you would look at it from the outside, it would be sort of stretched to almost infinity, and it would look like as if time comes to a standstill. And in fact, light would disappear. And because if light disappears, everything else would actually disappear as well. And so at some point, there is this virtual membrane that we now call the event horizon, which separates the inside of a black hole from the outside. Of course, at the time, these things were not called black holes, but they were just mathematical curiosities, and even the term event horizon didn't exist. But the consequences of this were quite profound when they were discussed very, very quickly, because it would mean that no information would ever be able to leave that space, even though it would exist. And so it would be sort of the end of physics, because, what is physics if you can't do an experiment? What our theories were if you can test them with measurements. And so, in fact, Albert Einstein didn't believe that these objects would be really existing. In fact, he didn't believe black holes would exist. So, when people nowadays say, we've proven Einstein right, it's not quite true. We actually proven him wrong. We've proven his own equations right, not his own interpretation of reality. Of course, the question was, how can black holes form? And can they exist? So Einstein wrote a paper to say, no, they cannot form. Oppenheimer said, very quickly later wrote a paper and said, yes, they can form by sort of a collapsing dust cloud, essentially a collapsing star. And nowadays we know that stars actually do collapse at the end of their lifetime in giant supernova explosions. And that means that their central cores will be condensed so strongly that gravity wins. Gravity is the smallest of all forces. But if you have many particles close together, and gravity only works in one direction. That's the big difference with all the other forces. They all pull in the same direction. Then gravity can win over all other forces. And in the very center of these supernovae, exploding stars, a massive neutron star can form. And if the star is very, very big, whatever is left in the center will keep collapsing forever, so that it becomes a smaller and smaller object, and collapses into an infinitely thin point. And we have very good evidence that this process exists and these compact objects are being formed. And then these are stellar mass black holes. They are made out of stars, and sort of you can get black holes of a few times the mass of the sun, to tens, to several tens we've seen by now. But then in the very center of galaxies, you have millions and millions of stars in a very, very small region. And that means you're also going to have a huge amount of big stars, small stars, but also the remnants of stars, black holes or neutron stars. And so if you form one larger black hole it will start to sink towards the center, as will many of the others. And they will coalesce, they will merge and become just bigger, because everything can just go inside. And matter and stars can also just go inside, and it will make this black hole grow. The exact processes, how this happens, we're not exactly sure, but it's a quite normal process. Whatever you do will only make whatever is the center of this galaxy just bigger. And so it's quite natural to think that if black holes exist, in the center of galaxies, you'd have a very, very big one. Of course, we didn't start with that thought. This was an afterthought after there was some evidence that there are dark objects in the centers of galaxies. And that came with the discovery of quasars, very, very luminous objects at billions of light years distance, where the light of an entire galaxy was coming from a region that was just, the size of, somewhat larger of our solar system, essentially. And so that begged the question, how can you get so much energy into such a small region? And how do you avoid this energy being blown away by its own radiation forces? And the answer was, well, the most simplest answer to explain these quasars is a supermassive black hole. A black hole of 100 million, perhaps even 1 billion times the mass of the sun. It has enough gravity to keep that energy in place. And the matter that falls in will actually gain a huge amount of energy. And then if you dissipate that energy, it can heat, it can radiate. So even though black holes are supposedly black, they can produce a lot of energy. And when people looked at nearby galaxies, they thought, if there were these supermassive black holes powering quasars at billions of light years distance, which means billions of light years in the past, then there should be still black holes in the midst of our galaxies today. And so if you now look at galaxies in our neighborhood, in the cosmic neighborhood, tens to hundreds of million light years away, and you measure the kinematics of stars and dust in the very center, what you find is that they're rotating faster than they should in the very center, just based on how much stars you see there. And so the conclusion was there is a dark mass in the center of galaxies. And what you found is, and what one finds is that the bigger this spheroidal component of a galaxy is, the bigger the central dark mass component. And so interpreted more or less, this means the bigger a galaxy, the bigger its supermassive black holes. And if you want to, and what I always wanted to see, when I started my PhD, I wanted to see black holes. Seeing is believing in science. And people were talking about black holes, but it wasn't clear where they will really exist. They seem to be way too small in the centers of galaxies. So is there a chance to actually see them? And the answer that arose slowly during and after my PhD is yes, it may be possible. And where would you look? So where are the best galaxies to look at? Well, if you look at the biggest monster galaxies, these are elliptical galaxies, then the closest one in our neighborhood is the galaxy M87. It's 55 million light years away. It sounds very far, but actually is very close to us. And if you calculate the size of its black hole with the mass that we have today, then it's about, we'll come to this later, it's about sort of 50 microarc seconds, the size of a mustard seed in New York as seen from the Netherlands. And then, of course, the other galaxy, which is smaller than this big one in M87, but is much closer, is the Milky Way galaxy. That is our galaxy, and so we are circling around the center, so we'll never be closer to any other galaxy than our own, obviously. And there's evidence for a black hole of 4 million times the mass of the sun. This is a completely different regime. This is 1,500 times smaller, 1,500 times lighter. It also is 100,000 times less matter falling onto it. So astrophysically, it should be a completely different regime. So that's why it's interesting and important to compare those two ones. And it turns out, if you look at what is sort of the size on the sky of the black holes, then both of these galaxies, of these black holes, are roughly the same size. This one is 1,500 times bigger, but it's also 2,000 times further away. And so that compensates exactly so that they, next to each other on the sky, that looks like they have the same size. So, what do we know about this one galaxy, M87? As I said, this is an elliptical galaxy. So there's, thousands of billions of stars in this configuration. It's the center of a cluster. That's how it became so big, because many other galaxies were merging, and this were making the galaxy bigger and also central black hole bigger. It was found here very early on. In fact, around the time that relativity was developed, there's this little streak of light coming out here. And today, we know this is a plasma stream coming out of the very center of that galaxy. And radio astronomy showed the true nature of this beast. When you look at it, there's, this it looks like a fire hose shooting out here, out of this galaxy. And then, this is an image made with a LOFAR, the low frequency array, a LOFAR telescope in the Netherlands, and actually extending all throughout Europe. And you see that the entire bubble, 100,000 of light years of this galaxy, is filled with hot gas that's actually all coming from the very, very center. And the idea is that this is a supermassive black hole there. And then the other galaxy, much more tiny, still hundreds of billions of stars rotating around the center. We are in the edge, in the disk of the galaxy, so we're looking through that disk. Unfortunately, our view in the optical towards the center is blocked by dust clouds, which are sort of in this disk of the galaxy. So with your bare eyes, you'll never see towards the black hole, the center. But you can switch to a near-infrared vision, and that you do with telescopes. And then you can actually look through the dust clouds. And what you see is actually, a central region, lighting up with stars that, it's extremely dense. And if you look really into the heart of the galaxy, what you see here are stars moving. And one of these stars actually moves on a 16-year orbit on a perfect ellipse. So like the planets orbit around the sun, this star orbits around the center of the Milky Way. But then with 5,000 kilometers per second, it's going around down here. And that means you need enormous amount of gravity there to keep this star when it makes its turn. It's very fast turn around. And you can calculate very directly what that mass is. It has to be 4 million times the mass of the sun. And that's work that Andrea Ghez and Reinhard Genzel did in 2 different groups. And that's what gave them the Nobel Prize, because it showed very clearly there is a dark mass in the very center, concentrated in one point. And what is this point? Well, that point was already discovered in 1974. This is a radio image, one of the recent radio images from the center of the Milky Way. That's a plane of the Milky Way, and radio images, radio light also go through the dust that there is in the center of the Milky Way. And if you zoom in here, then you see that there is this sort of a streamer of gas, and in the very, very center, there's a small small source, a small object emitting radio emission from a very small region. And that source is called Sagittarius A star. Sagittarius A, A means the brightest radio source in the constellation Sagittarius, and the star just means it's a very exciting source. So that's how the name came about. And this was always suspected to be the supermassive black hole. And that's the one actually I worked on during my PhD, because it turned out nobody had actually a good understanding where the radio emission came from. And we developed a model for that radio emission to understand. And what we realized was that a certain type of radio emission, namely high frequency millimeter waves at around 1 millimeter wave, 230 gigahertz, would come from, if that's a black hole, would come from near the event horizon. And that's something that excited me when we did these calculations, essentially pen and paper, and that already very clearly showed, there is light coming from really near the darkness of the event horizon. And that is important, because how do you want to see a black hole, right? So that's a black hole on a dark background. There's not much to see. You need to shine light at it. and then some interesting aspects will happen, and that's the light bending. And so you know here you shoot light rays at a black hole, and you see how it's bent. It goes around. In fact, light can even go on a circle around a black hole, and that's what we see here. So the light is coming in, and if you just shoot it at the right angle, it will actually be bent onto a circle and remain there forever, which essentially means there is a sharp divide. Every light that comes in from a little bit closer will be bent around but end up in the event horizon. So if you look at it from this direction here, you actually look into the event horizon. Sometimes not directly. Sometimes you look around it and then look at the back, but you're still looking into the event horizon. While it's outside, your vision or your light ray will sort of go around, and you may look at some distant star. You may even look at yourself again if you're really very, very, very lucky. But you're not looking at the darkness. And that actually produces a very characteristic and fundamental signature. It took me a while to realize this, what this meant. But sort of this realization that, well, wow, there's light. And then the second one, wow, there's this light bending which actually captures light from further out and leads to actually a magnification of the event horizon. Was really a very memorable moment, sort of, at least the point I still remember when I sort of first realized, wow, that's happening. So maybe we can actually use radio astronomy techniques to actually see the event horizon directly. And so we calculated that. I mean, first you do it again with pen and paper, and you have some conceptual understanding, but then you have to do a proper calculation. And this was a paper that we published in 2000. This was more or less the end of sort of a long process of 5-6 years, but also became the beginning of something new. And this was, how a black hole would look like that is surrounded by light. And our model was actually that you have optically thin, a transparent, glowing plasma around the black hole. In fact, for the experts, we calculate sort of this emission in the jet outflow, which would be sort of engulfing the black hole from all sides. So you radiate light at all sides, and then what you see is this dark region here, and that's where from all the light that disappears in the event horizon, and then around it you see this ring of light, which comes from all the radiating gas around it, and from the light bending around the black hole. It also means, as I said, that this light bending makes the event horizon look larger. So the actual black hole may be small, the event horizon, in sort of a physical dimension, but since the light is captured further out, that darkness is actually larger. And it turns out whatever you do to the astrophysical model or to the black hole, that size of the shadow, as we called it in this paper, the shadow of a black hole, is more or less directly proportional to a mass. If you know the mass, you know exactly how big the shadow should be, and you could measure it with the proper techniques. And and to understand what that shadow really is, or what you're seeing is, I always like to give a very simple everyday example, like a wick in a candle or a teapot in a campfire. You have bright glowing gas which you can look through. You can look through the light of a candle, and you're going to see the wick in the very center, or this teapot. You see the light around, but the teapot here is blocking the light that comes from behind. And the same is happening with the black hole. It's just blocking the light, it's absorbing the light, and it's magnifying itself a little bit. That's sort of a second effect that's doing. Of course, we have to do more than just these simple models. We also try to understand how black holes work, and that's why in the last decades, very detailed simulations have been developed for black holes. And so we do is essentially calculating how hot gas, magnetized gas evolves around a black hole. That's what you see here. There's a torus of gas, and the threads or sort of magnetic field lines, and then it rotates around the black hole. The magnetic field lines are being stretched, and they actually make the matter, they break the matter a little bit and make it fall towards the center. And if you keep running this, you'll actually see that in the very central region, black holes are spun up and shoot out along the rotation axis of the rotating gas. And that produces these powerful jets that we see in M87. You then add in the simulations radiation to it, and you calculate how matter emits and absorbs light. Here we calculate this in a more popular representation, but it's real, all kinds of physics sitting in here. But this calculating all frequencies together, and so you see this. You saw this disk of gas and the plasma shooting out. Now, if you then focus on the frequencies that are emitted near the event horizon, so you're just seeing essentially the flame surrounding the wick, surrounding the teapot. Then what you see is that sort of a paper, from 2016, where we predicted how M87 should look like. You see this dark shadow in the center and this ring of light where light is being bent around. And again, the size of the shadow is very clearly predicted by a theory of general relativity. And so, it took about 20 years from this experiment, from the proposal of this experiment, to actually realizing it. But in 2017, we did this. The first observations with the Event Horizon telescope, which uses a very long baseline interferometry principle. Sorry, there's still a German word in here, this principle. So that's not a new idea, but you had to go to the highest frequencies that hadn't been tried before, at least not in terms of imaging. And so the principle is very simple. How does it work? You need in order to see a mustard seed in New York from Europe, you need an Earth-sized telescope. And you do this by synthesizing a large telescope. What you can do is you can actually store the light waves, which are radio waves, in telescopes around the world. And then everything else a dish does, namely focusing, you do later in a computer. So, if you'd had a big dish, what would it do? Let's look at two places here on Earth. One here in Spain and one on the South Pole. Two light rays from a point source would come in, that would be reflected on that dish and then brought together in the focus. If you just have, if the dish would be just reflecting on these 2 points, you would only see these two waves coming in, be bundled together in the focus and overlap. And that would give you, because both are waves, and both would be, because its point source would be sort of identical waves, would give you an interferometric pattern. So you have a plane wave coming in, you have essentially two slits here, that's how you would see them. You would interfere them, and then you get interference patterns. And this is, so somehow my internet connection seems to be a bit slow. I hope it's better for you. Anyway, so that's what you would see. And this is what we do see. So this is a simulation here. You have two sources. You're looking at one object in the sky, which is almost a point source. Not exactly. It has some shape, as you will see. You bring them together, and what you get in the end is an interferometry pattern. But now we have actually more antennas, more points on your dish that you bring together, that you reflect, again, later in the computer. You bring them together, and all these interference patterns put together will actually give you an idea of the shape of the source. Again, a teacup or teapot in this particular case. Of course, the more you have, the better the image would be. But we only have a few, and so the image will naturally always be a bit ugly and not perfect. But you can use image reconstruction and cleaning algorithms to actually improve that. And that's exactly what the Event Horizon Telescope did. It was organizing a campaign, and we had sort of 300 scientists around the world. This is from our collaboration meeting in Nijmegen in 2018, where we actually discussed the results of this. We were organizing the campaigns. We had teams sent to different telescopes. We had, and in fact, I realized, I think I took out the slide with the telescopes. I apologize. That's now there may be a chance later to show them. We organized a campaign, and then we went to the data analysis process. And that was a very difficult process because this was the first time we had done it, and it was a very high-profile result. We split up into different teams to actually independently calibrate the data, independently image the data, independently analyze the data, and use sometimes 2 or 3, sometimes even 4 different types of software to actually do this. And then, the first image was presented in 2019, and you will see this zoom here that we made, zooming into the center of M87, the image that we presented in 2019. This is the biggest zoom in astronomy, a factor 1 billion that you see here. And you see the radio image showing up from LOFAR, and then you have the Hubble image of the jet sticking out, and then we're going to higher and higher radio frequencies with VLBI images, and you see the jet coming out of the center. You always see the jet until you go to the Event Horizon telescope frequencies, and you see that. So that was the first image we made, and it would look completely different from all the other VLBI images ever made of this source and actually other sources of similar types, but it had this characteristic ring-shaped feature, and it had the darkness in the very center. And the size was fitting exactly the prediction of what you would expecting for a supermassive black hole of this size. So that was an amazing moment to see, and to me almost unexpected that it worked at the first attempt. We had 4 different days which all showed the same result. We had multiple different image reconstruction algorithms. And by now there are three or even 4 papers now sort of reproduce the data. We made all the data public, so that is publicly available, and they've actually confirmed this. There's now 1 paper coming out, I think, who claims they have not found it, but this is essentially we've checked that due to a flaw in their analysis. So I think that's a very, very solid result, but also a clear prediction, because if that's a black hole, if that's how it should look like, it made a prediction for various properties. For one, this ring should be more or less stable in terms of size, and that's something. And that is something we checked. We went back to old data where we didn't have enough telescopes. We only had 3 or 4 telescopes. That wasn't enough to do images. But once you have an image, you can check whether your image is consistent with the data and whether the size has changed. And all the data of the past 10 years are essentially consistent with the same ring of the same size. So that's a key prediction of this. We of course have more data. We have 2018 data that we have analyzed and that we're going to publish, and so that we'll be able to shed further light on the consistency of those results. We also looked into the polarization of light. The polarization of light is light has, is a wave, and it can oscillate in a plane, in 2 actually orthogonal planes to each other. That's something you do not see, but you can measure. Photographers have polarization filters, and then they can choose whether they want to see reflected light of a mirror or look through the window, for example. And in radio astronomy, you can also measure the polarization of light, which was this hidden property. And that's what you see here with these shapes that show the direction of the polarization of the oscillation plane. And it's slightly tilted. And that directly can translate into a orientation of the magnetic fields, because the magnetic fields around which particles radiate or gyrate and will produce radiation, they produce the polarization of the light. They give a certain direction of the oscillation of the light. And if we take that measurement and compare it to our models, it confirms the picture that we have in M87, that the magnetic fields, as I said, are wound up and then are sticking out out of this plane of the rotation of the gas. And that's a consistent picture that we have. So we are seeing now how magnetic fields are behaving near the event horizon, and how these powerful quasars and supermassive black holes are actually powered using this galaxy nearby home as an example. And the second prediction, of course, apart from understanding this and the stability, is that this picture of M87 should have an equivalent in the center of our own Milky Way. And so that was another independent test of our interpretation and the techniques that we have. And so in 2017, we also observed the center of the Milky Way. And it took a little longer, and I'll briefly say why. But let's first look at the image, do the same zoom into the very center, and let's look how it looks like. This is the galaxy now in radio light. You see it actually glowing everywhere from exploding stars, supernovae, and hot stars. Then we zoom into the central few hundreds of light years, and we see Sagittarius A. This is actually an explosion that happened 40,000 years ago. The streamer again that you still remember, and here that's Sagittarius A star, where we never saw exactly its structure. And then we zoom in further and further and go to the last experiment, and finally again we saw that structure. And this was again another awesome moment to just see an old friend. An old friend because it was looking like we had expected it, but also because Sag A star was sort of the goal of our dreams always. That's what we want to see. We want to see in the heart of the Milky Way. And then once more, it had sort of a ring-like structure and sort of a darkness region here. And why did it take us so long to actually get this data out compared to the others? Well, we did all kinds of quality check. The first images we already made very early on. So already 2018, we had a feeling, well, this is, that's where it's heading. But quantifying the error and quantifying all the possibilities that you have was a major challenge. And the big problem is that Sag A star, the center of the Milky Way, our galaxy, is 1,500 times smaller, as I said. Everything rotates around the black hole with almost the speed of light. So it's 1,500 times shorter length scale in absolute numbers, but orbiting with the speed of light. And that takes, in the center of the Milky Way, 5 minutes or 15 minutes. While in M87, this actually is the movie. It moves, it rotates. But it takes two weeks. It takes 1,500 times longer. And so M87 was standing still while Sag A star was changing, or the galactic center was changing every 5 minutes. And we see that here. This is an image with lower resolution of actually during our observations. This year, again, this is what's called the mini spiral. And this light here is coming from the black hole. It's flickering. It's going up and down. And you see this here in this light curve. And it's actually happening on time scales of 50 minutes. So in that we had to quantify. So what we did is just to make sure that our images were right, we actually started with simulations. And so these are all kinds of simulations which sort of fit the basic properties of the radio source that we saw. You see sometimes it's a ring, sometimes it's a double source, sometimes it's a disk. And we ran that through different imaging algorithms that you see here, 4 different ones. And we asked them to actually reproduce the simulations with a certain set of parameters. And we only took imaging parameters that were reproducing all types of sources or source structures equally well for all the different algorithms. So there's sort of a big consensus, democratic data reduction, sort of the superset of all parameters that are able to reproduce all the different images were used. I mean, you can tune your algorithms to just reproduce, to be more efficient for rings. We didn't want to do this, right? So we want to be equally efficient for all different types of structure. That's very important. That's what we did. And we had to take the noise into account, the variability. And so we quantified that as a noise contribution. We had to give it a number, and so essentially just giving it a number took a year or more. And then we made, using this set of parameters that were all good, all were equally good. We made sort of thousands of images, all slightly looking different, but this you see here in this cloud in the background. but they all have sort of a basic feature in common. They're sort of roughly the same size, actually pretty much the same size, and there's darkness in the center. And if you just take the democratic average, that's the image you get in the end. And that's an image over, the variability of Sagittarius A star and the different parameters. And that's why, there are these three different features here. They're not necessarily exactly there because, during the time of the experiment, it could have, they certainly would have moved a little bit and so forth. So that's the average picture of many hours. And then, okay, I'll skip that part. And then what we did, we used simulations. Different simulations. We calculate literally millions of images of black holes. And you see here different images, and you see them here. This is how black hole looking from the side, and here it's how it's looking face on. And so you see a slightly difference because here it's more asymmetric than here. Here it's more symmetric. And that has to do with the rotation because that's going with the speed of light. And if matter comes towards you, then it will be actually amplified by what we call relativistic beaming. So it becomes brighter on one side. And then we changed other parameters. So in this case, it's more jet dominated, as we say. So the emission is coming more from the jet. In this case, the emission is coming more from the outflow, and this is coming more from the inflowing matter, the radiation. So it's slightly different location where the radiation is being produced in the gas. And then we compare this with our data. And let me see if that works. Okay, now I forgot to start the movie. So you have this huge set of simulations, which, by the way, almost all show this dark region, which is quite amazing. Then you look at the size of the ring, and that only rules out a few of these simulations. But then you look at the asymmetry, for example, and the thickness of the ring, and actually many other models fall away. And then you look at the broadband emission, how much emission is emitted in the X-rays and in the near-infrared and in the radio, then actually more models fall away. And then you look at sort of, does it explain the VLBI emission or the earlier measurements at lower wavelengths? And then in the end, only 2 of these models survive, but they do survive. And they seem to be able to capture and reproduce the basic properties of Sagittarius A star. And that tells us basic properties of the source. So the model here, it may not be the ultimate truth, but the best fitting model, sort of the winning, the beauty contest winner of all these models has, has a strong magnetic field. It has a jet outflow also in the center of our Milky Way, but it's pointing towards us. And that's sort of the amazing part, that this black hole, seems to be pointing towards us. In this model, the black hole seems to be spinning itself, and the magnetic fields are able to extract energy from the rotation of the black hole. And the accretion rate, and I, already in my PhD thesis, I call this source a black hole on a starvation diet because it wasn't feeding that much. And that's also confirmed in these modeling here. It's roughly 1 moon every 3 years. Now, sounds a lot to you, but given that other black holes actually feed on 1 sun per year, this is actually rather little. And so, for the first time now, we're getting really a good understanding of the astrophysics of black holes. But most importantly, and that's what impresses me the most, is just a simple property of the shadow. As I said, if you look at the mass, you can directly predict what the shadow size is. So all you need to know about a black hole is its mass. It has hardly any other properties. Yes, it can spin, but for the shadow, even that doesn't really matter. So tell me the mass, I tell you how big you are. And then, you measure M87 and it's spot on this red line, which is sort of not a fit, it's sort of a prediction of it. And then you may have heard of the gravitational wave measurements that were made of stellar mass black holes, and I think they got a Nobel Prize even a couple of years ago. And no, I know, but I don't know how many years ago. and you can actually, and it's interesting to realize, and that's a realization that came later, that the gravitational waves that are emitted from these mergers of stellar mass black holes are produced at exactly the same shadow region that we are observing. Because also gravitational waves follow the optics of the light bending. And then you can calculate the shadow size also from the gravitational waves. And it's measured with pretty much the same accuracy. And then you go factor 100 million lower in mass, and the size of the shadow is properly reproduced by the gravitational waves. Of course, 2 lines you can always fit 2 points you can always fit a line, and that's where the galactic center comes in. That was the third measurement. And given we had our method tested with M87, it was clear it would come in this region here, and it had to be of exactly the determined size, and it was. And I find this quite amazing to see. These are 3 completely independent measurements, and they fall within 20% over factor 100 million exactly on this line. And that really is the power of general relativity, which seems to only care about mass. These are so different types of black holes. It's amazing that this works. It's also amazing that our models, the astrophysical models, are able to reproduce nowadays all these properties that we see. We have more data. As I said, we had more data in 2018. We also had more observation in 2021, and the latest one from 2022. We had more telescopes here in France, NOEMA, Greenland telescope, and in Kitt Peak in Arizona. With joining, we had so we'll be able to get much better images from M87 in the future. We still want to have better images, certainly for the center of the Milky Way. We are missing telescopes in the southern hemisphere, because the galactic center is a southern source. It's seen best from a location in Chile or here in Namibia. That's where the galactic center is directly overhead. And so we are trying to put a telescope now into Namibia, and certainly in the first few hours, this is what you get in the first 5 hours with the current telescopes. But if you then add just one more telescope, you suddenly, already in the first 5-6 hours, you're able to produce a reasonably good image with the data that you will have then. And then we hope to make a movie, essentially. We couple this in Namibia with actually a mobile planetarium that goes to all the schools, and that has was stopped during Corona, but it's now restarting. And that's, I think, a quite exciting outreach project that's coupled to the telescope project, and it's done together with the local university, as is the other in Windhoek, as is the telescope project. In the long run, I'll be very quick now. We'll want to go to space. One idea is to have like 3 dishes going around Earth, and as they orbit in 4 hours around the Earth, they will actually drift apart slowly, and then you get all separations, all orientations, and so you measure essentially all components of the image very well. And for M87, this is at 230 gigahertz. You can make movies at high resolution. In fact, you can go to higher frequencies, can make even better movies. And so, as I said, this is just the beginning of what we are able to see. In fact, if we want, all black holes with this radio mission, we would be able to see if we really would want to. Of course, it's a question of money in the end, how many we want to see and what the science case is. But certainly going an order of magnitude, or 1 to 2 orders of magnitude higher in resolution, will definitely completely transform the way we understand black holes. And I think in the end, we'll understand black holes better than our own sun, in fact, which is sort of, an interesting thing, because the sun is more complicated than a black holes are simple. So let me conclude. So the Event Horizon telescope has seen the shadow now twice. So I think we can firmly say supermassive black holes are real. We see the shadow. The shadow is the signature of the light bending in the Kerr metric and absorption by the event horizon. It's the 2 effects combined. We see that relativity holds over 8 orders of magnitude. It does not have a preferred mass scale, which is, bad news for many of these alternative models, which do have that. And we see that sort of accretion flows are magnetically dominated. They produce powerful jets, even in a source like Sagittarius A star. It seems they also extract energy, spin energy from the black hole. Though these conclusions are subject to the uncertainty, to the fact that you believe our astrophysical models, and it's phase-on. The phase-on orientation, I think, is much more robust because it depends on the symmetry, and you can make these arguments based on very simple basic GR arguments. In the future, we'll have more telescope, better images. We go to space, and I think what I find amazing is, having started 30 years ago when black holes were sort of still fantasy, very far away. We're now imaging. We're imaging the direct environment. We're seeing them merge, hearing them merge. So really now in an age of experimental space-time physics, and as we did, particle physics, the last century. Now we're doing space-time physics with big experiments. And who would have thought that 100 years ago when this all started? Thank you.
Thank you. Now we have time for questions, so you can write them in the chat or ask to be unmuted. There was already one question in the chat, so you already discussed how the black holes in the centers of the galaxies are formed by accreting material. There's a question, will the Milky Way eventually end up in a black hole?
Partially. Stars will certainly go in there. Every 10,000, 100,000 years, a star will end up in the center of the Milky Way. But most stars will be shot out into interstellar space. There will be a merger. Andromeda and the Milky Way will merge. And so that will drive some gas and stars into the central black hole. But it's hard to say which ones. So whether our star will end up in the black hole or somewhere out into the dark and cold space, we don't know. Most will probably escape the black holes.
Thank you.
But these are long time scales, so don't be worried now.
Thank you. There's another question. The central black holes of M87 and Milky Way have the largest angular diameters in the sky and are hence the best candidates for observation with the EHT. But are there any other galaxies whose central event horizon shadows come close to those 4 or 5 microarc seconds? Or are we, so to say, stuck studying just the supermassive black holes of these two galaxies?
If you stay on the ground, you're stuck with those. Yeah, maybe you can build an optical interferometer, but then you have to build something like the 10, 20 meter dishes and put them kilometers away, and that's not on the horizon yet. But if you go to space, the one I showed you, you have quite a few more. And in fact, the longer you make your baseline, the separation, so the further out you go into space with your configuration, the more you can see. In principle, you could see black holes all the way out to the beginning of the universe. There are some very massive black holes in the very early universe, which you could see. But yes, I think, and that's exciting. That's why these past years are so exciting. That's the first time we've seen supermassive black holes, but it's also going to be the last time for a few decades until we go to space, I think.
Thank you. Do we have questions from on site, Esko?
So apparently no questions from the live audience.
Then I have a question, which is that can you say what's the meaning of this triangular or roughly triangular structure that you see in the Milky Way around the Milky Way black hole, that you have these 3 particularly bright spots in the accretion?
Yeah, I was briefly referring to this in the talk. So what we can measure very well, if you have a ring, we can measure very well its diameter. But where exactly on that ring the brightest intensity is very difficult to see. Let me try to see whether I can go back to the slide I went over. I skipped. Maybe that takes too long, unfortunately. Let me see. So let's see this one here. Yeah, that was a bit stupid. So yeah, let's see this here. So these are all different ways of making the image. That looks, and you can cluster all the thousands of images you can make, and what you see is that that they look slightly different. So in some cases, this one here this blob is much brighter. In this case, which is a rare case, the third blob is much weaker. So there's a lot is affected by the variability and also where our telescopes are. So we cannot equally, cover the entire ring, so to speak. So I wouldn't interpret too much into the fact that there are three. It could be just a coincidence of the day. So if you make one the other day, it could be that they're sort of slightly different location. If you move the telescopes around, that would be a slightly different location. That would still be in the ring. Yeah. So that's something else I wanted to say, which I forgot. But so I wouldn't be too hung up about what these rings tell you, what these points show you. But what's very significant is the fact that it's fairly symmetric. Yeah. So had this be an edge-on black hole, it would have been only possible to see one side, and then this blob you would have never been able to see. It would never have been able to see emission in this part of the ring or this part. So yeah.
I have one question. So was there any theoretical prejudice on the rotation axis of Sagittarius A? Was it just completely random and it just turned out to be oriented the way it was seen?
Yeah, very good question. I had a prejudice. That's why I didn't like it, because we had this model that the radio emission is made in the outflow, yeah, in the jet coming towards us. And there was always the question, and it fits almost every observation, all properties of Sag A star, and it's very naturally fits that. Except you don't see the jet. You don't see, like in M87, you don't see it sticking out. There's some good reasons why it should be shorter, but it would have been easier to not see it if it's face on. That's why I didn't like it, because I didn't want to make our model depend on a very special orientation, right? But then the group of Reinhard Genzel, they were looking at near-infrared emission. They saw some gas going around. They don't see the shadow, but they see something going around the black hole as well. And it's also symmetric and also has some polarized structure. And they said, well, it probably is more face on. And so that was a surprise. People didn't quite took with a grain of salt, but that's what the data showed. Then there was some 3 mm data which also suggested this was face on, and now we have the symmetric image which also suggests it's face on. So it's the data now driving us to this orientation, and I'm now accepting. I'm happy because that solves all the problem, the final problem that we had with the jet model. But it's still weird. It's still weird. Because it means it points into the galaxy where we are, more or less. Maybe pointing slightly away. It's not exactly at us, but so it's missing us. But it's roughly into our quadrant of the galaxy, and there's no prior or prejudice that it should be in this particular direction. However, what we know is from other galaxies which are much more active, in spiral galaxies, is that their rotation axis also pointing everywhere. It can be pointing straight up, but it can be pointing into the disk. There is no preferred axis whatsoever. And that's because gas can come in from all directions, and that's what determines the rotation axis of the accretion disk. So, yeah, I mean, it's a weird coincidence. M87 also points somewhat in our direction. So these two close to supermassive black holes both point roughly in our direction, it seems. And it feels a bit uncomfortable. But yeah, you know, things happen.
Thank you. Are there any more questions from the audience or from the chat?
There are no more questions in the chat.
So then we should all thank Professor Falcke for this excellent and highly interesting presentation, and wish the collaboration the best of luck for the future experiments. And hope to hear from them again in the near future.
There will be more. We'll take the time it takes, but there will be more.
So then our next speaker is Kaj Wiik. So Kaj Wiik is a senior research fellow at the Tuorla observatory in Turku, and he's a Finnish member of the Einstein Horizon telescope team. So he will tell us in particular about the Finnish participation and aspect to this experiment. Just a second, we will have to transform the talk into this computer first. Oops.
Joo, se on Ubuntu eli sieltä vaan.
Se avataan.
Joo, sieltä build.
And yeah, just a second.
Se on kyllä vaan se toinen.
Se on tuolla. Yeah. No. Okay. So can you still hear me?
Yes, we can.
Well, I hope you can. Okay, good. So let me try to get my presentation visible. And now if I share my screen from this.
Yes, we can.
Okay, good. So let's begin. So as I was saying, my name is Esko Keski-Vakkuri. I'm a University of lecturer of theoretical physics at the University of Helsinki, and my past research has been addressing some issues of quantum mechanics coupled with black holes. But I'm not going to discuss that today. I will just mention some motivation for that. So this is going to be some sort of a mini review of properties of black holes and what they are. So in fact, what is seen here is more or less the same picture as what Professor Falcke was showing earlier about the stars orbiting the supermassive black hole in the center of the Milky Way. Okay, so as was mentioned earlier, black holes, they sounded like science fiction, and even Einstein himself didn't believe that they could exist. And when I was a boy, there was this movie by Walt Disney Company called The Black Hole, and it sounded very exotic and very science fictionish at the time. And nobody was absolutely sure. At least most of the scientists were not sure whether black holes could be there, even if there was some indirect evidence. So you could make a list of things that sound like science fiction to you now, and store that list and get back to it 20, 30 years from now, and you might be surprised in a similar way. That now I'm surprised that now it's possible to take images of black holes. So the plan for this talk is to just review quickly what black holes are and some properties of them, and then some properties that allow you to observe them. So the basic idea of general theory of relativity is that mass and energy curve space-time, and then the curvature of the space-time guides the motion of particles and bodies and light itself. So in this way, the Earth curves well in space, and if you launch a rocket ship into the space, the rocket must first climb out of the gravitational well to escape Earth. For that, you need a sufficiently large initial velocity, and in fact, the velocity of the rocket must be larger than what is called the escape velocity, which is specific to every star and planet. And it was known a very long time ago, actually already in the 18th century, that if there would be a star, which would be so massive that the escape velocity would be faster than the speed of light. At the time, the speed of light was already known to be finite. So then light itself couldn't escape from the surface of that star, and therefore these stars were hypothetical dark stars that wouldn't be seen on the sky, and they could be very numerous without us having any idea about their existence. But there's a caveat to this line of thinking, because light is made of photons, which are massless particles, unlike a rocket. So Newton's theory of gravity doesn't quite explain how massless particles would need to climb out of this gravitational well. So for that you need the general theory of relativity, and now there's a more precise understanding that the well is really a geometrical shape of the space-time around matter, and this geometry is determined as a mathematical solution of something known as a metric that tells the geometry of the space-time from Einstein's field equation, which is the central equation of general theory of relativity. And sort of the input into this equation is the energy momentum distribution of matter, like that in a star. And very soon after Einstein's theory, Carl Schwarzschild found the first solution to these field equations, a spherically symmetric solution that looks like this sort of a well shown in the image. And it describes the geometry around a star or a planet. And moreover, also very early on, Oppenheimer and Snyder proved that if there's a star that burns out its fuel, if the star is sufficiently large, it will collapse under its own gravity, and this collapse has no end, so that you end up with an infinitely deep well, as shown on the right on this picture. But the name black hole is much later. It's usually attributed to the physicist John Wheeler in the 1960s. So here's a picture of the black hole again with the curved space-time, and inside there's something that we call the singularity. So what is a singularity? This is usually something that happens in classical physics. You know about the electric field produced by a point-like charge. And the strength of the electric field is inversely proportional to the distance from the charge. And if you go to shorter and shorter distances, the strength of the field approaches infinity. And just in a similar manner, the curvature of the space-time also approaches infinity at the center of a black hole. But in classical physics, these singularities are usually interpreted as signs of something missing from the theory. The theory is not complete. If it predicts infinities, then there must be something that explains and enhances your understanding that there must be some new aspects that explain away the infinity. And the favorite explanation is quantum mechanics, that classical physics is not sufficient, but you need quantum phenomena, and those become important at short distances. And for instance, modify our understanding of the electric field of a point charge so that we avoid infinities. And the same is hoped to be true about general theory of relativity, that once it's married with quantum mechanics, then it can be understood what replaces this concept of singularity in the middle of a black hole. So what is the border between the inside and outside of a black hole? A common analog is the following. Now consider a river that has a waterfall, and then there's a fish that is swimming upstream in the river, trying to avoid falling into the waterfall. But the fish cannot swim arbitrarily fast. It has its characteristic swimming speed that we call c here. But on the other hand, the speed of the water increases. The water flow becomes faster towards the fall. So at some point, if the fish goes closer and closer to the edge of the fall, at some point the water in the river is flowing so fast that the fish is bound to drift downstream towards the fall and cannot avoid its fate. So therefore, there's a point of no return that marks the boundary of how close to the waterfall the fish can go, so that it still can escape. Now, analogously, the horizon of a black hole is a similar point of no return for escape of light rays from the vicinity of a black hole. So the horizon marks the boundary of a black hole. The interior of the black hole is the region inside the horizon, and from that region, nothing, not even light, can escape. And the size of the interior depends on the mass of the black hole. For example, if the black hole has a same mass as the sun, then its radius is only 3 kilometers, whereas the radius of the sun is 700,000 kilometers. So by comparing these numbers, we see that black holes pack a lot of mass into a small region, which makes them extraordinary objects in space. So inside a black hole, there's supposedly this bottomless well. So you may ask, where did the mass go? And indeed, that's a very hard problem, and I will return to that at some point. But then on the other hand, far away from the horizon, the geometry of the space-time is exactly the same as that of a star that has the same mass. So therefore, we can now ask what would happen to the planets of the solar system if the sun would be replaced by a black hole with the same mass. And if you understood everything so far, then you would conclude that the planets would orbit just like around the sun, because the geometry at that radius is the same, and the geometry guides motion, and they would not be devoured by the black hole. Of course, life as we know it would anyway end, since it's supported by solar energy, which the black hole wouldn't have. Now, a star is held together by two balancing forces. On the other hand, it's made of gas which pulls itself inwards by its own gravity. But then on the other hand, there's radiation pressure from nuclear reactions in the star that pushes the gas outwards. Sorry for the mishaps in this sentence. So gravity pulls and radiation pressure pushes the gas outwards. And this radiation pressure is supported by nuclear reactions, but there's only a finite amount of fuel in the star. And so at some points, nuclear reactions start to fade out and the star begins to collapse. And if the star is large enough, then as shown by Oppenheimer and Snyder, then the star collapses into a black hole in the end, assuming that the star is completely spherically symmetric. Now this brings us to this concept of spherical chaos, known by physicists, that usually you assume your analysis by assuming things to be perfectly symmetric. But of course, in nature, nothing is completely spherically symmetric. So what about the realistic case when the collapsing star is neither spherically symmetric nor has uniform density? So then this was studied by Roger Penrose, and he proved in 1965 rigorously that in general relativity, even an irregular collapse leads to a black hole. And for that, he was awarded the Physics Nobel Prize in 2020. So how can one observe black holes? We already heard about that a lot. So let me just review some things. So suppose that there's a star close to a black hole, then gas coming from a star can fall into the nearby black hole. And as the gas falls into the black hole, then the fall releases kinetic energy, meaning you have ever faster collisions of gas particles in the gas, and these collisions heat it and eventually transform it into a hot plasma. And the temperatures may approach millions of degrees of Celsius. And then you have this hot plasma that radiates. Now, then the matter that is spiraling into the black hole and the plasma that emerges from it form a disk-like structure known as the accretion disk. And then on the other hand, plasma gives rise to a strong magnetic field. We already saw these images of field lines of the magnetic field. And they develop due to the rotational motion of plasma in the accretion disk, magnetic field lines form this kind of a funnel-like shape or a bottle-like shape that then directs the beam of charged particles and X-rays that emerge from the plasma into forming beams that are perpendicular to the accretion disk. And these beams of particles and X-rays can then be observed. So here's an image from the Hubble in the bottom. Then we also heard about the bending of light rays in space-time. So gravity in a way acts like a lens. So and in fact, this was the early experimental verification of general theory of relativity. It was an experiment of Arthur Eddington, where they took pictures of a star, and then during solar eclipse, the star was kind of close behind the sun, but since the light from the sun was blocked, they was then they took pictures and they were still able to see the star, even if it was not where it was supposed to be. And this was due to the bending of the light in the gravitational field, and things worked exactly like general relativity was predicting it to do, or more or less exactly. So when the light ray passes through this bent space-time, it travels a curved path, but when you look at the star, then you of course imagine as if the ray would have been proceeding in a straight line, and the same effect sort of fools your eye just when you are using ordinary lenses, that your brain kind of interprets the passage of light rays in a different way from what the actual path is. So this effect is known as gravitational lensing, and that's a very powerful tool used in astronomy. So here's again a picture of galaxies, and light from the galaxies is passing through some massive body, and then as a result we see this distorted image, and we can even see these ring-like structures of light, and this was predicted by Einstein very early on, but he was very doubtful whether this would be useful. So here's a comment from Einstein that first of all, you would have to be very lucky to be in a line between an object that is bending the light rays and then an object that you want to see, so that the image would be distorted like this. And then the resolution that you would need would not be within the range of, within the power of our instruments. So there's no hope of observing this phenomenon, but that is now a routine part of astronomical observations. So Einstein was proven wrong here as well. So we also heard about rotating black holes. Now, normally all these pictures are shown for non-rotating black holes, but in fact there are 4 kinds of black holes. They can rotate, and they can also have electric charge. And the electrically charged solution was actually co-found by Finnish Gunnar Nordström in 1910s. But the solution for the rotating black hole was much harder to find. So it took almost 50 years before this geometry was understood by Roy Kerr. Now, rotating black holes have a spectacular feature that now in classical Newton's gravity, the rotation of a body has no effect on the gravitational field, but that's not true in gravitational relativity, in general theory of relativity, where space-time is elastic, but the rotating mass kind of pulls the space-time with it, just like as an analogy, a rotating spoon in a jar full of honey would do. And even Earth, as it's rotating, pulls its own gravitational field, leading into an effect that has been observed in this Gravity Probe B satellite experiment. But there's an upper limit for the speed of rotation. You cannot rotate arbitrarily fast, but there's an upper bound on the rotation speed, velocity, or the angular momentum of a black hole. Now, the space-time structure of a rotating black hole is much more complicated. Now you don't have only one horizon, but you have 2. And the ring, the singularity has the shape of a ring or a hula hoop. Now then there's a region where bodies cannot beat the rotating motion, but you are kind of bound to rotate along with the black hole. And there's even a process that would mine energy from a black hole, known as the Penrose process. But some things are kind of less well understood, like this inner horizon that you don't directly experimentally probe. There's some debate about whether that's stable or not, and it's not known whether this is the last word on the structure of rotating black holes. But most black holes that we observe rotate, and indeed they can rotate very fast. Like here's an object known as GRS 1915 plus 105 in the Milky Way. It's a binary system consisting of a star and a black hole, and the black hole rotates very close to the theoretical maximum, which amounts to the mind-boggling 1,150 rotations per second, while at the same time it's quite massive, having 10 to 20 times the mass of the sun. But what these observations don't tell us, what is inside the black hole. So we have this problem of asking what happened to the mass of the star as it collapsed. Is there really empty space and then all the mass is kind of concentrated into something like a point? Or is there some structure behind the horizon? And so what exactly happens to the mass? And how do we need quantum mechanics to understand it? And how to then marry quantum mechanics with general theory of relativity? And there are some proposals that have been thrown around for having something else than an empty space behind the horizon, go by these exotic names with a firewall, fast wall, and a gravastar. And there is some hope that maybe if there is some structure, maybe it could have some yet unknown or understood effect that could eventually be observed by something like when two black holes collide. So now we have these new observational windows, and indeed we can see or observe collisions of black holes, because in these collisions gravitational waves are created, and these are waves in the structure of the space-time itself rather than waves in some medium. And the first direct observation of gravitational waves was made in the LIGO and Virgo observatories in 2017. And now they have since then seen many more events of that type. And we have this new way of combining observations so that we can even see black holes at centers of galaxies, like what we heard about today. Even seeing a black hole in our own Milky Way, which was just completely unthinkable at the time of this Disney movie, The Black Hole. So maybe there are many more surprises that we cannot even see yet to come in 30 years. Thank you.
Yeah, very sorry about the hassle. I could finish but participation in the EHT. Okay. EHT project. And I'm Kaj Wiik. I joined the collaboration only 2 years ago, and it was like jumping into a moving steam train, and they had worked for 3 years in secrecy and developed a lot of interesting new methods that I didn't know of. It was very interesting. And add to that pandemic. In fact, I have worked only in my kitchen and a little study in upstairs, and I haven't met any of the collaboration members except the two Finns a couple of times. So it's very strange setup. Okay, the Finns and people working in Finland are Tuomas Savolainen from Aalto and Metsähovi. His specialty is imaging and also physical interpretation of the images and results. And Venkatesh Ramakrishnan, in fact, he's from India, and he made his master's in Turku, in Tuorla, and I was his supervisor, and then defended his thesis in Aalto. and spent some years in Chile, and then returned to Finka, or Esko Keski-Vakkuri in Finnish. He takes care of observations at Apex, that's in Chile, at 5 kilometer altitude. Very challenging environment. You have to use extra oxygen in order to stay conscious. And they have to set up everything because the EHD observations are very different what they do normally there. So they take much of all the recording equipment, and they have to set up them and check that they work. Then he has done data calibration. I'll tell about that more later. Imaging and physical interpretation, and he's also the AGN working group coordinator. That means that EHD doesn't just observe Sage Star and M87, but also other sources. Also sources that we know that we will not observe a shadow, but still they are interesting, and still all have black holes in them, and that's why they are observed. Then Jan Wagner, he's from Finland, worked at Aalto, had his master's in Aalto, and now he takes care of data correlation in Max Planck bond correlator. That means that all the hard disks are shipped to Bonn, and also in Haystack from the telescopes, and then they are correlated in order to produce the data that we then can process. And then myself, I have done calibration, imaging, and physical feature extraction, meaning the size of the ring, basically. Okay, but I really have to say a couple of words of history of interferometry in Finland, because it's surprisingly deep. Sir Martin Ryle was awarded Nobel Prize of Physics for inventing aperture synthesis. And in fact, Jorma Riihimaa connected to that in quite interesting way. Here is the paper of phase-switched interferometer from 1951. Pay attention to the year. Here he describes a new type of interferometer, and this was one paper that was awarded by the Nobel Prize. Then, in fact, in Helsinki University, Jorma Riihimaa observed first fringes in weak fields. He built in his 20s antennas corresponded with Sir Martin, and did that 2 years after the paper, in 50s. No internet, you really couldn't call to England, just normal paper mail, and it's really interesting. And I have his correspondence with Ryle, and it was spectacular, I would say. Okay, then after the first fringes, it took 20 years, and he moved to Oulu and started decametric observations. and wrote a lot of papers of Jovian system and emission from there. And then 79 first tests in Metsähovi brand new 13.7 meter telescope at 5 gigahertz by Stefan Tallqvist. Then again, many years were going, and in 91 we built the first own receiver and recording equipment, and it used VHS cassettes, and the recording speed was 4 megabits per second. And in fact, the part of my thesis consists of these observations, so they were useful. So I mapped 15 AGNs using VHS cassettes. Okay, and in 93 we built from scratch a recording terminal, a high-speed recording terminal. It was a crazy project, but it was very interesting, and we all learned a lot about VLBI by doing that. Then, and this relates to EHT. We did first millimeter VLBI at 3 millimeter wavelength by the help of Juhani Peltonen, who was taking care of the receivers there. We retrofitted an old 3 millimeter receiver to work with VLBI, and really very important for the history of EHT. We did first 2 millimeter observations, and in fact 1.3 millimeters were tried first, but it failed, and then they went down to frequency and tested 150 gigahertz, and it was successful. And after that they started 1.3 millimeters, and after that in Metsähovi they have developed the technology for VLBI a lot. Okay, I'll continue. Then to EHT. Of course, like I mentioned, first we have to do the observations, and there are a number of telescopes, and at every telescope a special crew has to be sent. And Venkatesh was at the Apex telescope near the Atacama Large Millimeter Array in Chile, and of course this is very important. And nowadays we have more telescopes, and more telescopes means better image quality. Then we have the data. We have to calibrate it. It means that, for example, there is a rainfall somewhere, and that attenuates the signal. So we have to take it away, and we have to know if it's real signal or a problem in the equipment, and that requires some experience and good eye on the data. And this is example. We calibrated ALMA data using a reference source, and the problem was that hot air bubbles rise from the Atacama desert and gave phase and delay turbulence of some of the antennas, and the amplitude went down. And Ed Fomalont and I found out what was the problem in this case. And this is very small part, one special case, but the process was really iteration. We calibrated, then imaged. There's a problem. We found that okay, this telescope didn't work like we expected. Then we investigated what was happening, and of course we can't just change the data. We have to find out what was the problem and calibrate it in a better way. So calibration is very important. Then imaging, like Heino explained, in this kind of very high profile project, we have to be absolutely sure that the image is real, that we are showing. And because of that, we produced synthetic observations using the same setup like the real telescopes, and produced hundreds of thousands of images with different starting parameters. Many of the imaging algorithms have a lot of knobs to tweak, and they change the end result. And for example, in Finland, in Turku, we calculated 10 million images of synthetic data and also the real thing. And because of that, some small part of the mean image contains images made in Finland. Okay, this is quite complicated thing, and I won't go into the gory details here. But here, well, Heino showed this image. Here are the test data we used, and the goal was to find in the imaging algorithms the right settings of the knobs to produce image of any object, not only a ring, and not favoring a ring, on the contrary. So in this way, we could be sure that we are not forcing a ring in the image. In fact, nowadays, after the first M87 star image, there has been development of new, better algorithms that do not have knobs. You just give them the data, and they calculate the most probable image you can find. You can produce from that data, and that's very interesting. And I'm very happy to be in the team that develops these algorithms. And Tuomas Venki and myself were collaborating with these parameter surveys. And then, like Heino mentioned already, we had to calibrate the observations with the simulations to get the diameter and mass correct, and that also required a lot of computations. In fact, the maintainer of the Turku cluster sent me an email. What are you doing? You have been eating up all the CPUs for 2 weeks. When will you stop? What are you doing? I said that okay, I'm making black holes here, and then I'll stop next week. And then that I did. And that in fact I have to say that be happy to live in Finland, because computational resources are plentiful here. It's not in all countries, especially in USA. It's very expensive, and you have to have a lot of funds to get hold on this kind of things. And in Turku, you just ask for an account, and off you go. And CSC that I'm now using Mahti, it's almost as easy. So please use them. Okay, here maybe I don't know if the cursor is yeah, it's working. In fact, I participated in this plot, and it's only one plot, but it took many weeks of work. And it's only plot. There were many teams doing the same for other methods. And as you see, all the methods and all the teams produced almost the same result. So we are quite confident that we are in right tracks here. Okay, that's all from me, and we, like Heino said also, this is just a start. We have one first image. In fact, we have 3 observing epochs, 3 years already now, with very interesting data, and now it won't take 3 years to reduce them, but it will be faster, and what we are hoping that we could make some, perhaps not movies, but characterize the variability there. Okay, thank you. Questions in chat? Yeah. Mulla on arvailuja, mutta ne on arvailuja, että jos joku osaa kertoa tähän eksaktin vastauksen, niin unfortunately I missed.
Vieläkö data kuljetetaan kovalevyissä?
Yes, I try to read the. I didn't hear the. Yeah, very good question. Yes. Okay. Part of not in Event Horizon telescope, but other forms in VLBI, you can transfer the data using internet, but the sheer volume of the data for EHT is too large for that. And well, one telescope is in the South Pole, so there is certainly no internet there. and in fact, you have to wait at least half a year before you can ship the tapes from South Pole because of the weather. It's winter in there. So yes, hard disks are used, and volume was 3.5 petabytes total for the 2017 run, and it's increasing, and I think it will double or have doubled already. But after the correlation, you can average a lot, and then the data sets that we are working with, they are only a couple of hundred of megabytes. So you can I have worked on my laptop with them, so that's not a problem. Did this answer your question?
A clock. So
we should wrap it up. Yeah. Thanks for questions.
All right, so I guess we have used our allotted time for this, and I would like to thank all participants for participating, and we hope that we will have similar exciting opportunities to tell about physics of the space-time in the future as well. Thank you.